Good morning students. Today we are going to discuss about one of the important type of motion, that is called the simple harmonic motion. The object moves in different kinds of motions. One is called the translation motion. If the object is traveling in a straight line, then the type of motion is called translation motion. And if the object is moving in a circular path, then it is called the circular motion. Sometimes, for example, in this kind of motion, the object will move in a particular to and fro, that is back and forth motion. So this is a kind of simple harmonic motion. Let us see some important kinds of simple harmonic motion. Watch this video.
Simple harmonic oscillator. Consider the moving pendulum of a grandfather clock. When the clock is wound and set into motion, the pendulum will swing back and forth about a fixed position. We refer to this periodic back and forth motion across the same path as oscillatory motion. When displaced from its original position of equilibrium, our pendulum will experience a restoring force. This force, F, is directly proportional to the displacement, x. As a result of the restoring force, the pendulum will eventually return to its original position. However, due to the phenomenon of inertia, the pendulum will first swing back and forth several times beyond its initial position of equilibrium. When systems such as our pendulum exhibit this repetitive movement, they are said to be harmonic oscillators. If the restoring force, F, is the only force acting on a system, the system is a simple harmonic oscillator.
So in this case, if the object is initially at rest, then it will be in the main position. So that is the rest position. If the object is in motion, then it can reach a maximum distance, and that position is called the extreme position. So here in this pendulum can be in the mean position or it can move till the extreme position. So this kind of motion. And here one more important thing is the force acting on the object to restore its original position is called restoring force. And the restoring force is always proportional to the distance of the pendulum from its main position.
While the clock pendulum represents a horizontal oscillation, masses hooked to the end of linear springs serve as representations of simple harmonic oscillators.
So in this case, if we are attaching a ball in the spring, then if it is allowed in the vertical motion, then this is also an example for the simple harmonic motion.
We use a very basic lab experiment to observe the simplest mechanical oscillating system. First, hang a liner spring vertically from a stand and place it at the edge of a counter. Then attach an iron ball to the end of the springs so that both items hang just over the edge of the counter. As the spring hangs, you will notice a small amount of tension in it due to the ball's weight. While our spring is static, the system is considered to be at equilibrium. In this position, there will be no net force acting on the system. Now, gently.
So if the object is in the equilibrium position, there is no net force. But once, if you are keeping the object like this, in this direction, then there will be a restoring force. That force is called the spring force, which tries to restore the ball to its equilibrium position, which causes the simple harmonic oscillation.
Pull straight down on the iron ball, enough to noticeably move it from the resting position. As you release it, the equilibrium in the system will be displaced. Instantly, an elastic restoring force will act on the ball, pushing it back towards the state of equilibrium. The ball will accelerate and move back towards the equilibrium position. The closer that our ball moves to the equilibrium position, the more the restoring force will decrease. But the moving ball will first acquire momentum, moving it past the equilibrium position and constricting the equilibrium point. It will establish a new restoring force that will slow its movement and eventually stop it. From that position, the net restoring force will push the ball towards the equilibrium position, only this time in an opposite downwards direction that will again stretch the spring. The restoring force X is given by the equation F is equal to minus Kf.
So this is one of the important conditions in the case of simple harmonic motion. That is, the restoring force is proportional to the displacement. The minus sign indicates that the restoring force is always opposite to the direction of displacement.
X, where F is the restoring elastic force exerted by the spring. K is the spring constant, and X is the displacement from the equilibrium. Summary. A body executing a to and fro motion across the same path is known as a simple harmonic oscillator. In it, the force of motion is proportional and oppositely directed to the loop.
Okay, so this is the definition for the simple harmonic motion. That is, a body executing a to and fro motion across the same path is known as simple harmonic oscillator. And this is a condition for the simple harmonic oscillation. That is, the force of motion is always proportional to the displacement of the body from its equilibrium position. Okay. Now, I told you simple harmonic motion is a to and fro motion, and one of the special case for the simple harmonic motion, or the simple harmonic motion is executed by this simple pendulum. So the simple pendulum is nothing but it is an arrangement. Here we are attaching a bow with a thread like this. Okay, and
simple pendulum. The pendulum clock was invented by the Dutch scientist Christian Huygens in the year 1656. This invention was based on the investigations of the famous scientist Galileo Galilei. Galileo studied the moving chandeliers in a church and found that their motion was periodic. This means that the chandeliers took the...
There is a beautiful story behind the story of the time period of a simple pendulum. Galilei used the heartbeat to find out the time period of a candle in the church.
Same amount of time for each oscillation. The pendulum clocks are based on
the movement of chandelier, and the grandfather clock can be considered as the simple pendulum. Here we know that this is the main position, and here also this is the main position, and the object can move in between the extreme positions.
this principle. The time-keeping element of a pendulum clock is a swinging weight known as pendulum. The pendulum swings back and forth, taking the same amount of time for each oscillation.
So the time taken by the simple pendulum to move from the main position and to reach the extreme position, again it will reach the extreme position, then it comes to the main position. So the time taken for this complete oscillation is called its time period. Now we are going to derive an expression for the time period of a simple pendulum.
Let us derive the expression for the time period of a simple pendulum. A simple pendulum consists of a ball of mass m suspended from the end of a massless, unstretchable string of length L. When the ball is displaced from the mean position and released, it starts oscillating about its mean position. Let us now analyze the two major forces acting on the simple pendulum. One of these major forces acting on the pendulum is the downward force due to gravity. The second major force is the tension exerted by the string. The tension.
Okay. Now listen. The body is having a mass m, so it will be attracted by the gravitational force. So the force of gravitation, that is given as Fg. So Fg is equal to mass into gravitational place. Here the Fg is equated by the tension on the string. Okay, but if the object is in the extreme position, we can, if the object is here, so we know that this is the force due to the gravity, that is mg, and this is mg cos theta, since this angle is theta. So we can resolve the force mg into two, that is, one is along the tangent line, another one is along the radial line. So the radial force is mg cos theta or fg cos theta. This is equal to Fg cos theta. Fg cos theta or mg cos theta. So Fg is the gravitational force.
Is always directed towards the pivot point of the simple pendulum. We assume that there is no air resistance to the motion of the simple pendulum. When the ball is at its mean position, the downward force due to gravity is cancelled by the tension. When the string makes an angle theta with the vertical, the force due to gravity can be resolved into two components, the radial component and the tangential component. Since there is no motion along the length of the string, the radial component Fg cos theta is cancelled by the tension.
So here the radial component Fg cos theta is cancelled by the tension of the string. So that's the reason there is no movement or there is no motion along the radial line. So the movement is along the tangential line. So the tangential force Fg sin theta is responsible for providing the acceleration of this ball. So we have to consider only the tangential acceleration, that is Fg sin theta.
However, the tangential component Fg sin theta is not balanced by any other force. This tangential component of gravity acts as the restoring force. The restoring torque generated by the restoring force is given by the expression shown. The negative sign indicates that the restoring torque always acts to decrease the angle theta. For small values of theta, sin theta is approximately equal to theta.
So we know that when sin theta is very small, that is there is a limit, that is when theta tends to 0, sin theta will become theta itself. So we can write, instead of sin theta we can write theta itself.
If alpha is the angular acceleration of the pendulum at this point, and I is its rotational inertia about the pivot point, the torque acting on the pendulum is given by the expression shown. The rotational inertia of the simple pendulum about the pivot point is NL squared. On comparing the equation 1 and 2, we get the expression for the angular acceleration as shown. Since the simple pendulum is undergoing simple harmonic motion, its angular acceleration can also be represented as shown. Using the equation 3 and 4, we get the expression for the angular.
So by using these two expressions, that is, this is for the alpha, this is the alpha in the case of a simple harmonic motion, then we will get the value P is equal to, the equation P is equal to
And the
2
time
by
period
root of L
of
by
a
C.
simple pendulum. Note that the time period of the simple pendulum does not depend on the mass of the ball. It only depends on the length of the string and the acceleration due to gravity.
Okay, finally we come to the expression that is T is equal to 2 pi root of L by G. Now, from this expression, we come to know that the time period only depends on the length of the pendulum and also the gravity of the place. So it doesn't depend on the mass of the object or any other parameters, it only depends on L and G at the place. Now, we will derive this expression once again. That is, we have to consider a simple pendulum. So a small mass is attached to the pendulum, and which makes an angular displacement theta. And we know that, so this is the weight due to the gravity, that is mg. We can resolve this vector into two. One is along the radial direction, another is along the tangential direction. So this is called mg cos theta, and this is called mg sin theta. Since we know that the tension of the string P and L is the length of the string. Now we know that the tension is balanced by the radial force vector, that is mg cos theta. So they cancel each other. Therefore, the only available force is mg sin theta. So this mg sin theta is the responsible component for the acceleration of the ball. Okay. Then we can write the torque. Tau is equal to, we know that force into displacement. Force into displacement. Here force is mg sin theta. So we can write mg sin theta. Here the sin theta. Here the distance d is equal to the length of the pendulum. So we know that the torque is always opposite to the direction of force. That's why we have to add one negative sign here. So torque is equal to minus mg sin theta into a. Now we know that in the case of rotation motion, so since the bow is moving like this, so this is a case of rotation motion. So we can write the equation for the rotation motion, that is torque is equal to I into alpha, where I is called the moment of inertia and alpha is called the angular acceleration. And also in this case, I is equal to m L square. M is the mass and L is the length of the string or length of the pendulum. Now torque is equal to m L square into alpha. So torque is equal to m L square alpha, and torque for this expression we can write minus mg. So theta, if theta is very small, we know that. So when theta is very small, sin theta is equal to theta itself. Therefore theta into L. Now this is equation number 1 and this is equation number 2. If you are equating these two equations, we will get m. So that is ml square alpha and mg theta L. So m L square alpha is equal to minus mg theta into L. So we can cancel some components and we'll get, so we can cancel these two and m and m. So finally we get the value of alpha is equal to minus g theta divided by L. So this is expression for alpha. So in the case of simple harmonic motion, the equation for alpha, that is acceleration, is equal to minus omega theta, where omega is called the angular velocity and theta is called the angular displacement. Then now this is equation number 3 and this is equation number 4. We can equate the equation 3 and 4. So what we will get? So minus g theta by L is equal to minus omega square theta. So we can cancel these two. Finally we will get omega square. We can cancel the minus and also. Finally we will get omega square is equal to g by L. So omega square is equal to g by L, which implies that omega is equal to root of g by L. But we know that omega is equal to. So what is the relation between omega and time period?
Omega is equal to
2 pi by t. So if you are substituting the value here, then you will get root g by L equal to 2 pi by t. Therefore, if you are writing the expression for t is equal to 2 pi into root of L by g. So this is the expression for the time period of a simple pendulum. So t is equal to 2 pi root of L by g. So from this expression, we can also write the expression for gravity. So the gravity g is equal to, so we have to square on both sides. We have to square on both sides. Then we are writing the value, the expression for g. So g is equal to 4 pi square into L by t square. So in this case, so you have to understand that, so since the gravity is a constant, so the length is proportional to t square. So which means that when the length varies, length of the pendulum varies, the t also will vary. So these are things you have to remember. Now
Let us summarize what we have learned so far.
So we have learned the frequency of the simple pendulum, that is omega is equal to root of g by L, and also the time period for of a simple pendulum, that is t is equal to root of 2 pi into root of g, root of L by g. And the time period of a simple pendulum depends only on the length and gravity. Then time period of a simple pendulum is independent of the mass of the body. Okay. Now, just we will recap what we have learned. So we have learned what is simple harmonic motion. Then we learn what is simple momentum, so simple pendulum. Then we have to learn what is the concept behind the simple pendulum, and we have to find the expression for the time period of a simple pendulum. Then we have to express the motion of a simple pendulum represents the simple harmonic motion. Okay. So we know that a simple pendulum can be considered to be a bob of small mass suspended from a weightless, inextensible and flexible string attached to a rigid solid. So we know that this is called the mean position and these are the extreme position. Then we can derive the expression for the time period by taking the tangential and radial component of the force acting on the board. The force acting on the board due to gravity is mg. Then we can resolve that into two, tangential and radial component. Tangentially is mg sin theta, radially is mg cos theta, and this mg cos theta is cancelled by the tension of the spring. Therefore, we can write the mg sin theta is responsible for the acceleration of the ball or pendulum. By using the concept, we can find the expression for the time period of the simple pendulum. Okay. Now, so these are the questions. So can you find the expression for time period of a simple pendulum? So first we have to draw the diagram. From the diagram we can find out the force acting on this, force along the tangential line and force along the radial line. Then we can find out the expression for the time period. Finally, we can find out the expression for the time period. Now, the second question is, look at this. That is, the amplitude of a simple pendulum is doubled. If you are increasing the amplitude, what will happen to the time period, total energy and maximum velocity. So that answer is given, that is t is equal to 2 pi root of L by g. Thus, the time period is not affected by amplitude. It depends only on the length and gravity difference. Okay. So it depends only on the gravity and the length. Now, what will happen to the total energy? Total energy is equal to, we know that total energy is equal to E is equal to 1 by 2 m omega square and k square. See, energy is proportional to the square of the amplitude. So if the amplitude is doubled, what will happen to the total energy? Total energy will be 4 times. Total energy will be increased by 4 times. And what will be the maximum velocity? Velocity is proportional to amplitude. So if you are increasing the amplitude, it means that, so if you are increasing the amplitude, then what will increase? The velocity also will increase. But instead of that, if this is the amplitude, then the velocity will increase. So velocity is proportional to amplitude. So if the amplitude will double, what will happen to the velocity? It will be increased by 2 times. Okay. Now, similarly, the acceleration due to gravity. So here you have to do one calculation. So the acceleration due to gravity on the surface of moon is given by 1.9 meter per second square. If the time period on the Earth's surface is 4.5 seconds, what is the period of simple pendulum on the surface of moon? So what is the surface of moon? We know that the time period will change because the gravity is also changing. So on the surface of moon, we know that this is the equation, that is T is equal to 2 pi root of L by G. So on the surface of moon, the gravity will be less. Okay. So what, only 1 by 6 times of the gravity on the surface of Earth. So gravity will be less. So what will happen to the time period? Time period will be more. Okay. Okay, now I have some questions to you. So can you answer? So I'll switch on the timer. So time starts now. The time period of a simple pendulum.
That's not what we understand.
Okay, very good. Within 2 or 3 seconds you answer. Okay. So does not depend on the mass. Okay. So that's the answer. Now the second question. The acceleration of a particle which executes simple harmonic motion is. The acceleration of a particle which executes simple harmonic motion is. It will be maximum at the extreme points. Okay. Now the third question. The frequency of a simple pendulum is given by.
1 by 2 by root of 3 by.
Okay. 1 by.
2 by root of 3 by.
Okay. So that's the answer. Now, when the metallic bob of a simple pendulum is replaced by a wooden bob, what will happen to the time period? Remain the same. Why? Because we learned that the time period is equal to 2 pi into root of L by G. So that depends only on the gravity and the length. Doesn't depend on the mass of the bob. Okay. Next question. If the length of the simple pendulum is increased by 4 times, so if the length is increased by 4 times, what will happen to its frequency? So 4 options are there. The first option is 1 by 4 times the original value. Second option is twice the original value. Third one is 4 times the original value. Half of the original value. Okay. Half of the original value, because we know that we have the equation for the frequency. Frequency is equal to 2 pi 1 by 2 pi into f is equal to 1 by 2 pi into root of L by G. But so our question is frequency. So this is what time period. Then frequency is equal to 1 by 2 pi into root of G by L. So L becomes 4 times, then F becomes 1 by 2 of the original value. So the half of the original value. This is answer. Okay. Now, hope you understand what we have learned. Now we are going to just do some experiments from the lab books. Okay. So this is based on simple pendulum. So just remember the equation for the simple pendulum. There is time period for the simple pendulum. There is the equation for the time period of the simple pendulum is 2 pi root of L by G. Okay. Now, so we are doing a small experiment. So here the aim of this experiment is using a simple pendulum. We are going to plot L by T, L and T and L and T square graphs. So we are going to draw both graphs. Hence find the effective length of the second pendulum. So for that, this is the procedure. So we have to clamp a simple pendulum like this. Then we have to take a string of length about 100 centimeter. We have to clamp the split cork firmly in the clamp stand such that the line of separation of split cork is perpendicular to plane of motion of simple pendulum. Then we have to make sure that the oscillating in the vertical plane. So we have to be careful about this thing. Now we are going to take the readings for this. So observation part. So in the observation part we have to plot a graph. Then we have to do some calculation. See. So here the length of the simple pendulum is 0.95. And the diameter or radius of the bob is given by 0.05 meter. Okay. Now, okay. So here you get the time period of oscillation. We are taking 10 oscillations for the calculation of its time period. Okay, so please note this value. For 10 swings you get 20.36 for the first observation. So here we have to note this. Listen. In case of observation, here we have to enter the value. Length of the string is length of the string is 95 centimeter. So 95 centimeter. Then effective length
5 centimeter.
95.05 centimeter. Okay. 95 centimeter, that is 5 centimeter. Okay, 95.5. 95.5. The number of oscillation 10. Okay. So what is the time for the first one? 20.36. 20.36. Okay. Then we have to repeat the experiment like this. So we have to repeat the experiment. Okay. Again. Now it is 2, third oscillation, fourth oscillation. Now the time is 20.31. 20.31. Okay. So third also we have to repeat. Now for the time being we are taking only 2 readings. Then what will be its mean value? That is 20.33. Okay. Then what is the time period then? So we have to divide 20.33 divided by 10. So it will become 2.03. 2.03. Okay. Okay. Then what is square? That is t square. What is t square? 2.03 square. Approximately 4 point. Okay, 4.1. Approximately is equal to 4.1. So now we have the value for T length. This is length L 95.5 and this is 4.1. So 2.03 and 4.1. Now we are going to draw the graph for this. So if you are drawing the graph for this, we will approximately get the graph like this. So this is a graph for L versus T, and this is a graph for L versus T square. You know that I told you. So with G is equal to the time period is equal to 2 pi into root of L by G. So by using this one, by using lab edge, we can do the experiment like this also. Okay, so here we are concluding our session. So we have learned what is simple harmonic motion, what is simple pendulum, and how we have derived the expression. So this is the end of this. Thank you so much.